So welcome, and today we're going to be talking about uniform circular motion, and specifically we're going to be talking about problem 25. Now problem 25 is a question that asks us to have a 500 gram rock and a bucket. We're going to put that 500 gram rock into that bucket, and we're going to swing it in a 2.2 meter diameter circle. Now what they ask us to find is to find the minimum speed that the mass or the rock will have so that it will stay in contact with the bottom of the bucket. Now obviously we're going to change a couple of the variables, so instead of a 500 gram rock we're actually going to have a 100 gram mass. Instead of a 1.1 meter radius of the circle, we're going to actually have a 0.66 meter radius, and we're going to be swinging it like this. To give a quick little example, if I were to swing it like that. So that is what we're going to be finding out today. So I hope you enjoy.
Welcome. I'm going to be talking about how to theoretically solve this problem. As always, we start with F equals ma. I'm now going to draw the free body diagram for the bucket at the top of its circular arc. The only force acting on it is mg, or gravity going straight down. So we could replace F with mg. And since this is uniform circular motion, we could replace the a for acceleration with v squared over r. We are trying to solve for v, so the m's cancel out, cross multiply, you get gr, and then square root it. So square root of gr equals v. G is 9.8, r is 0.66 meters, and we've pre-calculated the answer, and it comes out to 2.5 meters per second.
So welcome. In the last video part, we learned that the velocity, or the minimum speed needed, is 2.5 meters per second. Now what we're going to do next is we're going to change this answer to radians per second. So what we're going to do now is we're going to use a wormhole equation. V equals r omega, and we're going to be solving for omega in this. So modifying the equation just a tad, we're going to have v over r equals omega. So plugging in what we know, we have a velocity of 2.5 meters per second, and we have a radius 0.66 meters. Now doing the fancy math and dividing that out, we get an omega of 3.9 radians per second.
Welcome. So in the last part, we determined that 3.9 radians per second was the minimum theoretical speed needed to keep the mass in the bucket. So we actually went outside and we tested this out, and what we did is we said that 2 pi radians equals 1 full rotation, and then we did some simple cross multiplication, and we determined that 1.6 seconds would be the period for 1 rotation. So we went outside and we had Eric rotate the bucket with a period of 1.6 seconds, and let's see what happens.
Get in position. Ready, set, go. Okay, that was perfectly 1.6.
All right.
So don't mess this up, go really slow.
All right.
Go. Where'd it go?
Here. All right.
Okay,
Super fast.
super fast. Oh shit! Okay.
So welcome one last time. As you saw in our video demonstration, we demonstrated 3 different times at 3 different speeds of swinging the mass within the bucket. Our first demonstration, we swung the bucket at a perfect 1.6 meters per second. Hey, Esmeralda. At the second demonstration, we rotated the bucket at a different much slower speed, and as you saw, the mass actually came out of the bucket. And for our final demonstration, we saw that when I swung the mass at a much greater speed than the 1.6 seconds, we actually lost the whole bucket mass system. So I hope you had a fun time learning about uniform circular motion, and as always, physics.